Couldn't care less.
Yeah. Huh?
Said I couldn't care less.
Wow, fair enough.
I think baseball's the most boring thing in the baseball world.
Okay, I can't do what? No.
Maybe it's because there's a million games a year. Golf is what?
Golf is very long.
I'm not gonna tell you.
I'm not getting caught, so I'm hanging it.
Either.
You know, Carlos got a big hole in
And then sometimes I have an accident, so it's
Alright. Like basically baseball, it takes about a half a month of break and then they're at it again.
Hey. Hey.
What?
Golf is boring.
Oh, golf is boring too, absolutely.
I find it. What about tennis?
I'd rather watch softball than
Yeah,
baseball.
Sports are
Yeah.
I like bowling fun. Tennis, squash. is
But
sport.
that's just 100% my personal opinion.
I like what you got.
I also think college football's awful.
What? I like
Yeah.
golf football.
I don't like football.
You don't like college
It's
football?
like watching a bunch of
I don't like sports.
fifth graders playing.
Wait, do you like that? Yeah.
It's like nobody can tackle, nobody can defend, and the scores are 100 to
I'd say like
88.
in college basketball, like defense is better than NBA.
Yeah.
Like they,
I actually like NBA better than college basketball now too.
yeah.
I don't like March Madness. I like March Madness better than.
I used to love March Madness. I used to make brackets all the time, and I think I've watched maybe 1 or 2 games the whole tournament this year.
Did you see the 16? See that?
No. I mean, I heard about it, but
That was pretty good.
I don't watch it.
It's Loyola.
Sorry.
The left-hand side.
Anyways.
It's Louisville.
Although you'll find as you get older, stuff like that becomes more trivial.
You're a Kansas fan?
Yeah, I grew up a Kansas fan. I grew up in North Dakota, and there was a player that was from North Dakota who was really good and played at Kansas. His name was Jeff Boschee. I don't know if you guys know who that is. He played with Kirk Heinrich and Drew Gooden. And they lost to Carmelo Anthony
Yeah, baby.
and the Syracuse in the final championship game. That was a heartbreaker. And so like I was in middle school when he was in high school, and so it was a big deal that, you know, North Dakota had this D1 star. Anyways, today we are going to move on to section B, where we spend a lot of time talking about the simple machine known as the lever. Okay? Quick review from the past couple days. What is work?
Applying for.
Oh, go ahead.
The exchange of energy for some change in the physical system.
Alright? Basically, using energy to cause a change in some physical system. Okay? There are four things. 3 things that are required for work to happen. What are they? Needs to be a force. Object must move. Yep, the object must move in the same direction as the force. So if you have a force perpendicular to motion, you have what? No work. Okay? What's the unit for work? Joule. Okay. Then we talked about power. What's power? Ah, look at you. The rate of work done. So the rate of doing work. How fast you're doing work. The more powerful the engine, the more work it can do. Okay. What was the unit for power? What? What? You don't know? Okay. Yeah. A watt. What else? Okay. What is the purpose of a simple machine? What does a simple machine not do? Okay, so if it makes it easier but doesn't change the amount of work, how does it make it easier? Lessens the force. Yeah, okay, lessens the force. How does it lessen the force? Okay, doing it over a longer distance. Good job. All right. Here we go. Forks and moments are equivalent.
Trying to do
Alright. What is a lever? There you go. Your last name. A lever is a rigid bar. What does rigid mean?
Not smooth.
Well, it can definitely be smooth. You're thinking maybe like there's I could understand where rigid might be. You could use rigid to say that it's rough as well, but not in the context of this. Okay. That's what a lever will do, but that doesn't really tell me what rigid means. Rigid just means isn't bendable. Stiff would be a good way of saying what rigid is. You're very rigid. You're stiff. At the end of a game, you're rigid. When the game gets close, you're rigid. Okay? And this is important because you wouldn't want to use something that bends as a lever, would you? If you're trying to pry a rock out of the ground, would you want to use a spaghetti noodle? No, probably not very effective. But a long metal bar, that might do the trick, right? Okay? Do you know what a fulcrum is? You ever heard the word fulcrum before? Okay? A fulcrum is the pivot point of the lever. So the fulcrum is right there. So if you want to write what a fulcrum is somewhere, you can just say it's the pivot point of the lever. You guys know what I mean when I say the pivot point, right? Where it rotates. Okay? Doesn't this look like a childhood memory? What do we call these?
Seesaw.
Oh, have you ever heard the alternate word? Teeter-totter. A teeter-totter.
Teeter-totter.
Okay? That is an example of a lever. We will talk about the 3 different types of levers later. There's a first-class lever, a second-class lever, and a third-class lever. A teeter-totter or a seesaw is a first-class lever. The fulcrum is in between the effort and the resistance, but we'll talk about that in a second. The fulcrum is the pivot point. Okay? Levers create rotational motion. Anything that has a pivot point has rotational motion. When you lock out this door, the door what?
Open.
Pivot.
Pivots, and so since it pivots, what kind of motion is this? Rotational motion. So that should maybe tell you that doors are actually a what? Lever. You guys know that? This is why when you try to go out the door to out the front doors, I always like push on the wrong side, and like it's really hard to open because I'm pushing like at the pivot point instead of at the furthest part from the pivot point. If that makes sense?
Oh, yeah.
How many times you walk out? I do that all the time. I walk out that front door and I push on the wrong side of the door, and it's like impossible to open.
Oh, open.
Yeah,
Okay.
because it's like I don't know. It seems backwards from where it should be, doesn't it? Or am I the only one? I guess I don't go out that door much anymore because I park it back. But okay. Rotational motion is anytime you've got a pivot point where an object rotates on. That's called rotational motion. Have you ever seen one of those doors that does the whole 360? You just go around and around and around and around and around, like Elf.
Yeah, yeah.
Now obviously the doors that we are used to experiencing don't rotate 360 degrees because it eventually hits a wall or something. So there are some limitations to some levers, and they may or may not be able to rotate 360 degrees. Have you ever got on a seesaw and got it to where you were at equilibrium? Where you didn't go up or down, you just kind of hovered? You know what I'm talking about? Okay? That's known as rotational equilibrium. And we're going to go way back to chapter 4, or 5. You guys remember Mr. Sir Isaac Newton? You remember Newton's laws? Remember when we talked about if the forces are balanced, our net force is 0, and therefore we are no acceleration. We could be not moving, but remember when we talked about we can be moving even if we have balanced forces? We're just not accelerating, we're moving at constant speed or velocity. So, if you have a teeter-totter or a lever with a fulcrum here, you could have the forces on either side balance each other out, and if your forces are balanced, you're not accelerating, and in this context, you would be at rest. Does that make sense? Now, let's say I get on one end, and Ethan gets on the other end. Are we going to be in rotational equilibrium? No. But could we by doing a slight modification? Any ideas what you could do to modify that, to get to equilibrium? Is that a whisper there, Abby? Do you want to say it out loud? You could add another person. I'm saying without changing our weights. You could move the fulcrum, but even better would be moving one of us. Okay? The heavier person, if you move closer towards the fulcrum, it's going to change what's called your lever arm. I'm going to explain in a second. Okay? It's the same idea of when you push on a door on the outside, it doesn't take a lot of force, does it? But when you push on a door on the inside, it takes a lot more force. So, Whether you're further or closer to the lever arm determines the amount of force applied. Does that make sense? Okay, and we are actually going to compute some of this stuff. So, the law of moments or torque. These words are equivalent. I will probably use torque more than moment, but they are equivalent. Okay, so I drew a picture of a door up here. Where's the pivot point on a door?
Left side.
Left side, right, on the hinges. So like there, there, and there. Okay, so that would be technically our fulcrum. Make sense? Okay? If I push on the door here versus here, okay, which place is it easier to rotate the door? On the outside. Experience tells us on the outside. So it says anytime a force acts perpendicular on a lever, we said the door was a lever, okay? On a pivot point, it produces a moment or torque. The torque is the product of the force and the distance from the pivot point. So this is the distance principle at work. The farther the distance from the pivot point, the less force, right? Didn't we say the force is reduced by doing it over a longer distance, right? That was the whole distance principle that we talked about yesterday. So, if the distance gets smaller, the force will be larger. And this is why when you go to the doors out in the front and you mess up what side you got to push on, it can potentially be a lot harder if you push on the side closer to the hinges. Does that make sense? Okay, good. Oops. Go ahead and get that. So the distance, and maybe, I don't know if I defined it. All right, so the distance from the fulcrum the distance from the fulcrum to where you're applying a force is called your torque arm or your lever arm. So this would be the lever arm for the for this force. This would be the lever arm for that particular force. The distance from your fulcrum to your force is called your lever arm. Right. There is our law of torques equation. Right there. Remember, what can I replace with this? Torque, and there's actually another word you can replace with that. Lever arm. I should probably just give you one instead of that. If you hear me say lever arm, it's the same thing as saying moment arm or torque arm. Actually, I will probably use a lever arm the most. And it makes sense since the variable for the arm is an L. I think the next slide is something really important. So before I go too crazy into this, I want to get Got it? Everybody? Good. Before I go too crazy to explain this, put this in. This has to be true in order to use that equation that I just gave you. This will not work if you're not at equilibrium. And if we're at rotational equilibrium, what does that mean? Yeah, it means you're not rotating in this context. So. Because you actually can have different forces and still be at equilibrium, but they have to have the same torque to be at equilibrium, which we'll see here in a second. All right, quickly. When we're at rotational equilibrium, that means that my lever is not rotating. Okay? It's balanced. So let's do a problem here. Yep. Where we have two girls that do not weigh the same amount. Whoopsies. Trust me, those girls aren't that big. One weighs less than 100 pounds. Remember, 5 newtons is a pound, approximately. All right, so we have a teeter-totter. Okay, we have a 600 Newton girl sitting on one side, 3 meters from the fulcrum, and it's asking where should you place the 400 Newton girl in order to balance the seesaw. Okay, first off, we have a 600 and a 450. Who can tell me which one needs to be closer to the fulcrum? 600. Okay? So let's say the 600 girl is here, and the distance they said was what? 3 meters. So we have the 600 Newton girl approximately there at 3 meters from the fulcrum. And what's the fulcrum? The pivot point. Is the ceiling enjoyable to look at there? All right, and we want to know, all right, where do I need to put the 450 Newton girl? What is the distance that I would have to put her at so that I am balanced? Does that make sense? So we are going to use our moment law of moments. Weight of the first times the lever arm equals weight of the second times the second lever arm. Okay, and what did we say the lever arm was? Okay, but what is a lever arm? No. Distance from that. The sheep over there? The fulcrum. It's the distance from the fulcrum to where the force is applied. So, we'll go, let's do some variables here. W2, L2. Okay? We're going to say that our first girl is our first situation. Okay? What's the weight of the first girl? Okay? What's the lever arm, or the distance between the girl and the fulcrum? And the weight of the second girl? And we are trying to figure out where we need to place that girl so that the teeter-totter is what? Balanced, or we're at rotational equilibrium. So, let's plug in and solve. 600 times 3 meters equals 450 times L. How do we solve for L? Now remember, this is what I've seen students do a lot. I've seen, stop, everybody, stop. I've seen students do this a lot. I've seen students bring this and over here and take 450 divided by 603. That brings everybody to the L side. We want everything away from the L side. Divide by 450 cancels it out, leaving you with L alone. That's why we divide this by the 450. When you do that, what do we get for the lever arm? 4 meters. Yes? Okay. If I put the 450 Newton girl anywhere else, would we be at equilibrium? No. The teeter-totter, or the seesaw, I always forget the seesaw, will not, or will be moving. Okay. We won't do that. We're done. You guys were engaged.
Beautiful.
Yes, sir. Thank you, sir.
Kramer,
Yes.
so we'll get a win tonight.
No way. No way.
If you go to the game,
I did play with it. We didn't miss.
really? Because you.
But remember, the place doesn't mean that you actually did good.